The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So last time we started looking at a system of spins. So there was a field S of x on the lattice, and the energy cost was proportional to differences of spins on two neighboring sites, which if we go to the continuum became something like gradient of the vector S. You have to integrate this, of course, over all space. We gave this a weight k over 2. There was some energy cost scaled by kt of this form, so that the particular configuration was weighted by this factor. And to calculate the partition function, we had to integrate over all configurations of this over this field S. And the constraint that we had was that this was a unit vector, so that this was an n-component field whose magnitude was 1. Okay? So this is what we want to calculate. Again, whenever we are writing an expression such as this, thinking that we started with some average system or we did some kind of a coarse graining, there is a short distance cutoff implicit in all of these theories. Now, what we can do is imagine that this vector S in its ground state, let's say, is pointing in some particular direction throughout the system, and that fluctuations around this ground state in the transverse direction are characterized by some vector pi that is n minus 1 dimensional. And so this partition function can be written entirely rather than fluctuations of the unit vector S in terms of the fluctuations of these transverse Goldstone nodes pi. And we saw that the appropriate weight for this n minus 1 component vector pi has within it a factor of something like square root of 1 minus pi squared. There's an overall factor of 2, but it doesn't matter. And essentially, this says that because you have a unit vector, this pi cannot get too big. You have to pay cost here, certainly not larger than 1. And then the expression for the energy cost can be written in terms of two parts. There is the gradient of this vector pi, but then there's also the gradient in the other direction, which has magnitude square root of 1 minus pi squared. So we have this gradient squared. And so basically, these are two ways of writing the same thing. Okay? So we looked at this. We said that once we include all of these terms, what we have here is a nonlinear theory that includes, for example, interactions among the various modes. And one particular leading order term is if we expand this square root of 1 minus pi squared, it will be something like pi square root of pi. So a particular term in this expansion has the form pi grad pi multiplied with pi grad pi. Of course, there are higher order terms. Okay. So a particular way of dealing with these kinds of theories is to regard all of these things as interactions and perturbations with respect to a Gaussian weight, which we can compute easily. And then we can either do that perturbation straightforwardly or from the beginning do a perturbative RG, which is the route that we chose. And this amounts to changing the short distance cutoff that we have here, that is A, to be B times A, and averaging over all modes within that distance, short wavelengths between A and BA. And once we do that, we arrive at a new interaction. So the first step is to do a coarse graining between the range A and BA. But then steps 2 and 3 amount to a rescaling in position space so that the cutoff comes back to be A, and the corresponding thing in the spin space, so that we start with a partition function that describes unit vectors, and after this transformation, we end up with a new partition function that also describes unit vectors, so that after all of these three procedures, we hope that we are back to exactly the form that we had at the beginning, with the same cutoff, with the same unit vector constraint, but potentially with a new interaction parameter k. And calculating what this new k is after we scale by a factor of p, the parts that correspond to 2 and 3 are immediately obvious, because wherever I see x, I have to replace it with bx prime. And so from the integration, I will get a factor of b to the d. From the two gradients, I would get a factor of -2. So the step that corresponds to this is trivial. The step that corresponds to replacing s with zeta s prime is also trivial, and it will give you zeta squared, although I have yet to tell you what zeta is. We'll do that shortly. And finally, the first step, which was the coarse graining, we found that what it did was that it replaced k by a strongly, sorry, didn't expect this. All right. With a factor k, which is larger by a certain amount. And the mathematical justification that I gave for this is we look at this expression, and we see that in this expression, each one of these pi's can be a long wavelength fluctuation or a short wavelength fluctuation. Among the many possibilities is when these two pi's that are sitting out front correspond to the short wavelength fluctuations. These correspond to the long wavelength fluctuations. And you can see that averaging over these two will generate an interaction that looks like gradient of pi lesser squared, and that will change the coefficient over here by an amount that is clearly proportional to the average of pi greater squared and that we can see in Fourier space is simply 1 over k q squared or kk squared for modes that have wave number k. So if I, rather than write this in real space, I write it in Fourier space, this is what I would get for the average. And in real space, I have to integrate over this k, appropriately weighed, between the wave numbers lambda over v and lambda. And this is clearly something that is inversely proportional to k. And the result of this integration of 1 over k squared, we simply gave a name which was I sub v of v. Because it depends on the dimension, it depends on, etc. So, yes?
Shouldn't there be an exponential inside the integral? An exponential inside the integral.
Why should there be an exponential inside the integral?
Oh, I thought we were Fourier transforming.
Okay, it is true. When we Fourier transform for each pi, we will have a factor of e to the ik. If we have 2 pi's, I will get e to the ik, e to the ik prime. But the averaging will set k and k prime to be opposite each other, so the exponentials disappear. So always remember the integral of any field squared in real space is the same thing as the integral of that field squared in Fourier space. This is one of the first theorems of Fourier transformation. Okay, so this is a correction that goes like I d of t. Okay. And last time, to give you a kind of visual demonstration of what this factor is, I said that it is similar but by no means identical to something like this, which is that a mode by itself has very low energy, but because you have coupling among different modes, here for the Goldstone modes of the surface, but here for the Goldstone modes of the spin, the presence of a certain amount of short-range fluctuations will stiffen the modes that you have for longer wavelengths. Now, I'm not saying that these two problems are mathematically identical. All I'm showing you is that the coupling between the short and long wavelength modes can lead to a stiffening of the modes over long distances because they have to fight off the wrinkles that have been established by shorter wavelength modes. You have to try to undo them, and that's an additional cost. Okay? Now, that stiffening over here is opposed by a factor zeta over here. Essentially, we said that we have to ensure that what we are seeing after the 3 steps of RG is a description of a theory that has the same short distance cutoff and the same length, so that the 2 partition functions can be mapped onto each other. And again, another visual demonstration is that you can decompose the spin over here to a superposition of short and long wavelength modes. And we are averaging over these short wavelength modes. Because of that, we will see that the effective length, once that averaging has been performed, has been reduced. It has been reduced because I will write this as 1 minus pi squared over 2 to the lowest order. And pi squared has n minus 1 components. So this is n minus 1 over 2. And then I have to integrate over all of the modes, pi alpha of k, in this range. So I'm performing exactly the same integral as above. So the reduction is precisely the same integral as above. Okay? So the 3 steps of RG perform for this model to lowest order in this inverse k, our temperature-like variable, is given by this formula once I substitute the value of zeta over there. So you can see that the answer k prime of b is going to be b to the d minus 2 zeta squared. Let's write for zeta squared, essentially the square of that, 1 minus n minus 1 over k. The 2 disappears once I square it. ID of b divided by k. That comes from zeta squared. And from here, I will get a plus ID of b over k. And the whole thing gets multiplied by this k. And there's terms that are order of temperature, or 1 over k squared. Okay. And finally, we are going to do the same choice that we were doing for our epsilon expansion, that is, choose a rescaling factor that is just slightly larger than 1. Yes?
Sir, you're n minus 1 over k times ID over k.
Yep, I did this too much. Thank you. Okay, thank you. And we will write k prime at scale b to be k plus delta L dk by dl. And we note that for calculating this ID of b, when b goes to 1 plus delta L, all I need to do is to evaluate this integrand essentially on the shell. So what I will get is lambda to the power of p minus 2, the surface area of a unit sphere divided by 2 pi to the d, which is the combination that we have been calling k sub t. Okay? So once I do that, I will get that dk by dl. Okay, what do I get? I will get a d minus 2 here times k. And then I will get these two factors. There's n minus 1, and then there's 1 here, so that becomes n minus 2. I have a IDB, which is kd, lambda to the d minus 2. And then the 1 over k and k disappear. And so that's the expression that we have. Yes?
So is the kd the solid angle factor again?
Okay. So we have to do this integration, which is written as the surface area, the solid angle, k to the d minus 1 dk divided by 2 pi to the d. This is the combination that we have always called k sub t.
Okay.
Okay? Now, it actually makes more sense, since we are making a low temperature expansion, to define a t that is simply 1 over k, again dimensionless. And then clearly dt by dl is going to be minus k squared dk by dl, minus 1 over k squared. Minus 1 over k squared becomes minus t squared dk by dl. So I just have to multiply the expression that I have up there with minus t squared, recognizing that tk is 1. So I end up with the recursion relation for t, which is minus d minus 2t, and then becomes plus n minus 2 kd lambda to the d minus 2t squared. And presumably there are higher order terms that we have not bother to calculate. So this is the thing that we will focus on. Okay. So let's see whether this expression makes sense. So if I'm looking at dimensions that are less than 2, then the linear term in the expression is positive, which means that if I'm looking at the temperature axis, and this is 0, and I start with a value that is slightly positive, because of this term, it will be pushed to larger and larger values. So you think that you have a system at very low temperatures. You look at it at larger and larger scales, and you find that it becomes effectively something that has higher temperature and becomes more and more disordered. So basically, this is a manifestation of something that we had said before, Mehran-Wagner theorem, which is no long-range order in D less than 2. Okay? Now, if I go to the other limit, D greater than 2, then something interesting happens in that the linear term is negative. So if I start with a sufficiently small temperature or large enough coupling, it will get stronger. I will go towards an ordered phase. Whereas the quadratic term for n greater than 2 has the opposite sign. This is n greater than 2, and pushes me towards disorder, which means that there should be a fixed point that separates the two behaviors. Any temperature lower than this will give me an ordered phase. Any temperature higher than this will give me a disordered phase. And suddenly we see that we have potentially a way of figuring out what the phase transition is, because this T star is a location that we can perturbatively access, because we set this to 0, and we find that T star is equal to D minus 2 divided by n minus 2 kd lambda to the D minus 2. So now, in order to have a theory that makes sense in the sense of the perturbation that we have carried out, we have to make sure that this is small. And so we can do that by assuming that this quantity, D minus 2, is a small quantity and making an expansion in D minus 2. Okay. So in particular, T star itself, we expect to be related to transition temperature, not something that is universal, but exponents are universal. So what we do is we look at d by dl of delta t. Delta t is, let's say, t minus t star in one direction or the other, no matter. And for that, what I need to do is to linearize this expression. So I will get a minus epsilon from here. And from here, I will get 2 n minus 2 kd lambda to the d minus 2 t star times delta t. Okay. I just took the derivative, evaluated the t star, and we can see that this combination is precisely the combination that I have to solve for T star. So this really becomes another factor of epsilon. I have minus epsilon plus 2 epsilon. So this is epsilon delta T. So that tells me that my thermal eigenvalue is epsilon. At this order, clearly independent of n. Now we've seen that in order to fully characterize the exponents, including things like magnetization, etc., it makes sense to also put a magnetic field direction and figure out how rapidly you go along the magnetic field direction. So for that, one way of doing this is to go and add to this a term which is h integral s of x. And you can see very easily that under these steps of the transformation, essentially the only thing that happens is that I will get h prime at scale d is h from the integration. I will get a factor of b to the d. From the replacement of s with s prime, I will get a factor of zeta. So this combination is simply my yh. And just doing a little bit of manipulation will tell you that yh is d minus the part that comes from zeta, which is n minus 1 over 2 id of b, which is lambda to the d minus 2 kd, and then we have t star. And again, you substitute for lambda to the d minus 2 kd t star on what we have over here, and you get this to be d minus n minus 1 over 2 n minus 2 epsilon. And again, to be consistent to order of epsilon, this d you have to replace with 2 plus epsilon. And a little bit of manipulation will give you a yh, which is 2 minus n minus 3 divided by 2 n minus 2 epsilon. I did this calculation of the two exponents rather rapidly. The reason for that is they are not particularly useful. That is, whereas we saw that coming from 4 dimensions, the epsilon expansion was very useful to give us corrections to the mean field values of 1/2, for example, for nu, to order of 10% or so already by setting epsilon equals to 1. If I, for example, put here epsilon equals to 1 to access 3 dimensions, I will conclude that nu, which is the inverse of yt, is 1 in 3 dimensions independent of n. And let's say for superfluid, it is closer to 2/3. And so essentially, this expansion, in some sense, is much further away from 3 dimensions than the 4 minus epsilon coming from 4 dimensions, although numerically you would have said epsilon, you put 1 to both of them. So nobody really has taken much advantage of this 2 plus epsilon expansion. So why is it useful? The reason that it is useful is the third case that I have not explained yet, which is what happens if you sit exactly in 2 dimensions. Okay? So if we sit exactly in 2 dimensions, this first term disappears, and you can see that the behavior is determined by the second order and then depends on the value of n. So if I look at n, let's say that is less than 2, then what I will see is that along the temperature axis, the quadratic term, the linear term is absent. The quadratic term, let's say for n equals to 1, is negative. And you're being pushed quadratically very slowly towards 0. The one example that we know is indeed n equals to 1, the Ising model. And we know that the Ising model in 2 dimensions has an ordered phase. It shouldn't really even be described by this because there are no Goldstone modes. But n greater than 2, like n equals to 3, the Heisenberg model is interesting. And what we see is that here, the second order term is positive, and it is pushing you towards high temperatures. So you will see a disordered behavior. And what this calculation tells you that is useful that you wouldn't have known otherwise is what is the correlation length. Because the recursion relation is now dt by dl is, let's say, n minus 2. I'm at d equals to 2, the lambda to the d minus 2 I can ignore. Kd is 2 pi from the solid angle divided by 2 pi squared. So that's 1 over 2 pi times t squared. Okay, so that's the recursion relation that we are dealing with. I can divide by 1 over t squared, and then this becomes d by dl of minus 1 over t equals to n minus 2 divided by 2 pi. I can integrate this from, say, some initial value, minus 1 over some initial temperature, to some temperature where I'm at length scale L. What I would have on the right-hand side would be n minus 2 over 2 pi L. Okay? So I start very, very close to the origin t equals to 0. So I have a very strong coupling at the beginning. So this factor is huge. T is small, 1 over t is huge. I have a huge coupling. And then I rescale to a point where the coupling has become weak. Let's say some number of order of 1. Order of 1 or order of 0. In any case, it is overwhelmingly smaller than this. How far did I have to go? I had to rescale by a factor of L that is related to temperature that I started with by this factor. Except that I forgot the minus that I had in front of the whole thing. So the resulting L will be large and positive. And the correlation length, the length scale at which we arrive at the coupling, which is of the order of 1 or 0, is whatever my initial length scale was times this factor that I have rescaled by b, which is e to the L. And so this is a exponential of n minus 1 over 2 pi times 1 over t. So the statement is that if you have in 2 dimensions a system of, let's say, 3 component spins, and that is something that has a lot of experimental realizations, you find that as you go towards low temperature, the size of domains that are ordered diverges according to this nice universal form. And let's say around 1995 or so, when people had these high temperature superconductors, which are effectively 2-dimensional layers of magnets. They're actually antiferromagnets, but they are still described by this theory with n equals to 3. There were lots of X-ray studies of what happens to the ordering of these antiferromagnetic copper oxide layers as you go to low temperatures, and this form was very much used and confirmed. Okay, so that's really the one thing that one can get from this analysis that has been explicitly compared to experiments. And finally, there's one case in this that I have not mentioned so far, which is n equals to 2. And when I am at n equals to 2, what I have is that the first and second order terms in this series are both vanishing. And I really, at this stage, don't quite know what is happening. But you can think about it a little bit, and you can see that if you are n equals to 2, then essentially you have a one-component angle. And if I write the theory in terms of the angle theta, let's say, between neighboring spins, then the expansion should simply be gradient of theta squared. And there isn't any other mode to couple with. You may worry a little bit about gradient of theta to the fourth and such things, but a little bit of thinking will convince you that all of those terms are irrelevant. So as far as we can show, there is reason that essentially this series for n equals to 2 is 0 at all orders, which means that as far as this analysis is concerned, there is a kind of line of fixed points. You start with any temperature, and you will stay at that temperature. Okay? Still, you would say that even if you have this gradient of theta squared type of theory, the fluctuations that you have are solutions of 1 over q squared, and the integral of 1 over q squared in 2 dimensions is logarithmically divergent. So a more correct statement of the Mermin-Wagner's theorem is that there should be no long-range order in d less than or equal to 2, because for d equals to 2, also you have these logarithmic divergence of fluctuations. So you may have thought that you are pointing along, say, the y direction, but you average more and more, and you see that the extent of the fluctuations in angle are growing logarithmically. You say that once that logarithm becomes of the order of pi, I have no idea where my angle is. There should be no true long-range order. And I'm not going to try to interpret this too much. I just say that Mermin-Wagner's theorem says that there should be no true long-range order in systems that have continuous symmetry in 2 dimensions and below. Okay? And that statement is correct, except that around that same time, Stanley and Kaplan did low temperature series analysis. Actually, no, I'm incorrect. Did high temperature series. Of these spin models in 2 dimensions. And what they found was, okay, we plot susceptibility as a function of temperature. We calculate our best estimate of susceptibility from the high temperature series. And what they do is, let's say they look at a system that corresponds to n equals to 3, and they see that the susceptibility diverges only when you get in the vicinity of 0 temperature, which is consistent with all of these statements that first of all, the correlation length only diverges at 0 temperature, and divergence of susceptibility has to be coupled to that. And therefore, really the only exciting thing is right at 0 temperature. There is no region where there is long-range order. Except that when they did the analysis for n equals to 2, they kept getting signature that there is a phase transition at a finite temperature in d equals to 2 for this XY model that described by just an angle. Okay? So there is lots of numerical evidence of phase transition. For n equals to 2 in d equals to 2. Okay? So this is another one of those puzzles. If we interpret the existence of a diverging susceptibility in the way that we are used to, let's say the Ising model and all the models that we have discussed so far, in all cases that we have seen, essentially the divergence of the susceptibility was an indicator of the onset of true long-range order, so that on the other side you had something like a magnet. But that is rigorously ruled out by Mehran Wagner. So the question is, can we have a phase transition in the absence of symmetry breaking? All right? And we already saw one example of that a couple of lectures back when we were doing the dual of the three-dimensional Ising model. We saw that the three-dimensional Ising model, its dual, had a phase transition, but was rigorously prevented from having true long-range order. So there, how did we distinguish the different phases? We found some appropriate correlation function, and we showed that that correlation function had different behaviors at high and low temperature, and these two different behaviors could not be matched. And so the phase transition was an indicator of the switchover in the behavior of the correlation functions. So here, let's examine the correlation functions of our model. And the simplest correlation that we can think of for a system that is described by unit spins is to look at the spin at some location and a spin at some faraway location and ask how correlated they are to each other. And so basically, there's some kind of, let's say, underlying lattice. And we pick 2 points at 0 and at R. And we ask what is the dot product of the spins that we have at these two locations. Okay? And clearly this is invariant under global rotation. What I can do is I can pick some kind of axis and define angles with respect to some axis. Let's say with respect to the x direction, I define an angle theta. And then clearly this is the expectation value of cosine of theta 0 minus theta r. Now this quantity I can asymptotically calculate both at high temperatures and low temperatures and compare them. So let's do a high T expansion. For the high T expansion, I sort of go back to the discrete model and say that what I have here is a system that is characterized by a bunch of angles that I have to integrate in theta I. I have the cosine of theta 0 minus theta r. And I have a weight that wants to make near neighbors to be parallel. And so I will write it as product over nearest neighbors, e to the k cosine of theta I minus theta j. Okay, so the dot product of two spins I have written as the cosine between nearest neighbors. And of course, I have to then divide by appropriate weight. Now, if I'm doing a high temperature expansion, that means that this coupling constant k scaled by temperature is small, and I can expand this as 1 plus k cosine of theta I minus theta j, plus higher orders in powers of k, of course. Okay. Now, this looks to have the same structure as we had for the Ising model. In the Ising model, I had something like sigma I, sigma j, and if I had a sigma by itself, and I summed over the two possible values, I would get 0. Here I have something like a cosine of an angle. And if I integrate, let's say, d theta 0 cosine of theta 0 minus something, just because theta 0 can be both positive as it just goes over the entire angle, this will give me 0. So this cosine I better get rid of. And the way that I can do that is, let's say I multiply cosine of theta 0 minus theta r with one of the terms that I would get in the expansion, such as, let's say, a factor of k cosine of theta 0 minus theta 1. So if I call the next one theta 1, I will have a term in the expansion that is cosine of theta 0 minus theta 1. Okay? Then this will be non-zero because I can certainly change the origin. I can write this as integral d theta 0 minus theta 1 I can call phi. This would be cosine of phi from here. This becomes cosine of theta 0 minus theta 1 minus phi. And this I can expand as cosine of theta 0 minus theta 1 cosine of phi plus sine or minus sine of theta 0 minus theta 1 sine of phi. Then cosine integrated against sine will give me 0. Cosine integrated against cosine will give me 1/2. So this becomes 1/2 cosine of theta 0 minus theta 1. Theta r. What did I do? For theta 0, I am writing phi plus theta 1. So this becomes phi plus theta 1 minus theta r. This becomes cosine of theta 1 minus theta r. This becomes theta 1 minus theta r. This becomes theta 1 minus theta r. Okay. So essentially, we had a term that was like a cosine of theta 0 minus theta r from here. Once we integrate over this bond, then I get a factor of 1/2, and it becomes like a connection between these two. And you can see that I can keep doing that and find a path that connects from 0 to R. For each one of the bonds along this path, I pick one of these factors, and this allows me to get a finite value. And what I find once I do this is that to the lowest order, I have to count the shortest number of paths that I have between the two. K, I will get a factor of k, and then from the averaging over the angles, I will get 1/2. So it would be k over 2. Let's see, by this we indicate the shortest path between the two. Okay? So the point is that k is a small number. If I go further and further away, this is going to be exponentially small in the distance between the two spins, where c can be expressed in something that has to do with k. So this is actually quite a general statement. We've already seen it for the Ising model. We've now seen it for the XY model. Quite generally, for systems at high temperatures, one can show that correlations decay exponentially in separation because it is the information about the state of one variable has to travel all the way to influence the other one, and the fidelity by which the information is transmitted is very small at high temperatures. So, okay, so this is something that we should have known. We are getting the answer. But now what happens if I go and look at low temperatures? So for low temperatures, what I need to do is to evaluate something that has to do with the behavior of these angles when I go to low temperatures. When I go to low temperatures, these angles tend to be very much aligned to each other. And these factors of cosine, I can therefore start expanding around 1. So what I end up having to do is something like a product over I theta I, cosine of theta 0 minus theta r. I have a product over neighbors of factors such as k over 2 theta I minus theta j squared if I expand the Gaussian, expand the cosine. And in the denominator, I would have exactly the same thing. Without this. So essentially, we see that since the cosine is the real part of e to the I theta 0 minus theta r, what I need to do is to calculate the average of this, assuming a Gaussian weight. So the theta is Gaussian distributed. Okay? Now, actually, this real, I can take the outside also. It doesn't matter. I have to calculate this expectation value. And this, for any Gaussian expectation value of e to the I some Gaussian variable, is minus 1/2 the average of whatever you have variance. And again, in case you forgot this, just insert a k here. You can see that this is the characteristic function of the Gaussian distributed variable, which is this difference. And the characteristic function, I can start expanding in terms of the cumulants. The first cumulant, the average is 0 by symmetry. So the first thing that will appear, which would be at the order of k squared, is going to be the variance, which is what we have over here. And since it's a Gaussian, all higher order terms in the series will. Another way to do it is to, of course, just complete the square, and this is what will come out. Okay? So all I need to do is to calculate the expectation value of this quantity where the thetas are Gaussian distributed. And the best way to do so is to go to Fourier space. So I have integral for each one of these factors of theta 0 minus theta r. I will do an integral d2q 2 pi squared. I have 1 minus e to the I q dot r, which is from theta 0 minus theta r, and then I have a theta tilde of q. I have two of those factors. I have d2q prime 2 pi squared. I have e to the minus I q prime dot r, theta tilde q prime. And then this average simply becomes this average. And the different modes are independent of each other. So I will get a 2 pi to the d, actually 2 here, a delta function q plus q prime. And for each mode, I will get a factor of kq squared, because after all, thetas are very much like the pi's that I had written at the beginning. Okay? So what I will have is that this quantity is integral over 1q's. Putting these two factors together, realizing that q prime is minus q, will give me 2 minus 2 cosine of q dot r divided by k q squared. So there is an overall scale that is set by 1 over k, by temperature. And then there's a functional form, which is the Fourier transform of 1 over q squared, which as usual we call C. We anticipate this to be like a Coulomb potential, because if I take a Laplacian of C, you can see that forget the q, the Laplacian of C from the cosine, I will get a minus q squared, cancels that. I will have the integral d2q 2 pi squared, cosine itself will be left. The 1 over q squared disappeared. This is e to the iqr plus e to the minus iqr over 2. Each one of them gives a delta function, so this is just a delta function. So C is the potential that you have from a unit charge in 2 dimensions. And again, you can perform the usual Gaussian procedure to find that the gradient of C times 2 pi r is the net charge that is enclosed, which is unity. So gradient of C, which points in the radial direction, is going to be 1 over 2 pi r. And your C is going to be log of r divided by 2 pi. So this is 1 over k log of r divided by 2 pi. And I state that when essentially the two angles are as close as some short distance cutoff, the fluctuations vanish. So that's how I set the 0 of my integration. Okay? So then you put that over here, you find that S0 dot S of R in the low temperature limit is the exponential of minus 1/2 of this. So I have log of r over a divided by 4 pi k, and I will get a over r to the power of 1 over 4 pi k. And I'm kind of want to check that I didn't lose a factor of 2 somewhere, which I seem to have. Yeah, I lost a factor of 2 right here. This should be 2 because of this 2 if I'm using this definition. So this should be 2, and this should be 2 pi k. Okay. So, what have we established? We have looked as a function of temperature what the behavior of the spin-spin correlation function is. We have established that in the high temperature limit, the behavior is something that falls off exponentially with separation. We have also established that at low temperature, it falls off as a power law with separation. Okay. So these two functional behaviors are different. There is no way that you can connect one to the other. So you pick two spins that are sufficiently far apart and then move the separation further and further away. And the functional form of the correlations is either a power law decay, or an exponential decay. And this form we know you have at high temperature. This form we know you have at low temperature. So potentially there could be a phase transition separating the distinct behaviors of the correlation function, and that could potentially be underlying what is observed over here. Okay? Yes?
So where do we make the assumption we're at low temperature in the second expansion?
When we expanded the cosines, right? So what I should really do is to look at a term such as this. But then I said that I'm low enough temperature so that I look at near neighbors, and they're almost parallel. So the cosine of the angle difference between them is the square of that small angle.
Thank you.
Yeah. Okay. So actually you may have said that I could have done the same analysis for small angle expansions, not only for n equals to 2, but also for n equals to 3, etc. That would be correct. That is, I could have made the similar Gaussian analysis for n equals to 3 also. And then I may have concluded the same thing, except that I cannot conclude the same thing because of this thing that we derived over here. What this shows is that the expansion around 0 temperature regarded as Gaussian is going to break down because of the nonlinear coupling that we have between modes. So although I may be tempted to write something like this for n equals to 3, I know why it is wrong. And I know the correlation length at which this kind of behavior will need to be replaced with this type of behavior, because effectively the expansion parameter became of the order of 1. But I cannot do that for the XY model. I don't have similar reason. So then the question becomes, well, how does this expansion then eventually break down so that I will have a phase transition to a phase where the correlations are decaying exponentially? And you may say, well, I mean, it's really something to do with having to go to higher and higher order terms in the expansion of the cosine, and it's going to be something which would be very difficult to figure out, except that it turns out that there is a much more elegant solution, and that was proposed by Kosterlitz and Thales. And they said that what you have left out in the Gaussian analysis are topological defects. Okay? That is, when I did the expansion of the cosine and you replace the cosine with the difference of the angle squared, that's more or less fine, except that I should also realize that cosine maintains its value if the angle difference goes up by 2 pi. And you say, well, I mean, neighboring spins are never going to be 2 pi different or pi different because they're very strongly coupled. Does it make any difference? Turns out that, okay, for neighboring spins it doesn't make a difference, but what if you go far away? So let's imagine that this is, let's say, our system of spins. And what I do is I look at a configuration such as this. Essentially, I have spins radiating out from a center such as this. Okay? There is, of course, a lot of energy cost that I have put over here. But when I go very much further out, let's say very far away from this plus sign that I have indicated over here, and I follow what the behavior of the spins are, you see that as I go along this circuit, the spins start by pointing this way, they go point this way, etc. And by the time I carry a circuit such as this, I find that the angle theta has also rotated by 2 pi. Okay? Now this is clearly a configuration that is going to be costly. We'll calculate its cost. But the point is that there is no continuous deformation that you can make that will map this into what we were expanding around here with all of the cosines being parallel to each other. So this is a topologically distinct contribution from the Gaussian term that we've calculated. Since the direction of the rotation of the spins is the same as the direction of the circuit, in this case, this is called a plus topological defect. There is a corresponding minus effect. Which is something like this. And for this, you can convince yourself that as you make a circuit such as this, that the direction of the arrow actually goes in the opposite direction. Okay? This is called a negative sign topological defect. Now, I said, well, let's figure out what the energy cost of one of these things is. If I'm away from the center of one of these defects, then the change in angle is small, because the change in angle, if I go all the way around a circle of radius r, should come back to be 2 pi. 2 pi is the uncertainty that I have from the cosines. So what I have is that the gradient of theta for between neighboring angles times 2 pi r, which is this radius, is 2 pi, and this thing that here it is +1, here it is -1. And in general, you can imagine possibilities where this is some integer that is like 2 or -2 or something else that is allowed by this degeneracy of this cosine. Okay? So you can see that when you are far away from the center of whatever this defect is, gradient of theta has magnitude that is n over r. Okay? And as you go further and further, it becomes smaller and smaller. And the energy cost out here, you can obtain by essentially expanding the cosine, is going to be proportional to the change in angle squared. So the cost of the defect is an integral of 2 pi r dr times this quantity n over r squared multiplied by the coefficient of the expansion of the cosine, RK over 2. And this integration, I have to go all the way to the ends of my system, let's call it L. And then I can bring it down, not necessarily to the scale of the lattice spacing, but maybe to a scale of 5 lattice spacing or something like this, where the approximations that I have used of treating this as a continuum are still valid. So there, I will pick some kind of a short distance cutoff A, and then whatever energy is at scales that are below A, I will add to a core energy that depends on whatever this A is. I don't know what that is. So basically, there's some core energy depending on where I stop this. And the reason that this is more important, because here I have an integral of 1 over r. And an integral of 1 over r is something that is logarithmically divergent. So I will get k. I have 2, cancels the 2. I have pi in n squared log of L over A. Okay? So you can see that creating one of these defects is hugely expensive, and energy that as your system becomes bigger and bigger, and we are thinking about infinite size systems, is logarithmically large. So you would say these things will never occur because they cost an infinite amount of energy. Well, the thing is that entropy is also important. So if I were to calculate the partition function that I would assign to one of these defects, part of it would be exponential of this energy. So I will have this e to the minus this core energy, I would have this exponential of k pi n squared log of L over A. So that's the Boltzmann weight for this. But then I realize that I can put this anywhere on the lattice. So there is an entropy gain factor. And since I have assigned this to have some kind of a bulk to it, has some characteristic size A, the number of distinct places that I can put it is of the order of L over A squared. So basically, I take my huge lattice and I partition it into sizes of A's, and I say I can put it in any one of these configurations. You can see that the whole thing is going to be e to the minus this core energy, and then I have L over A to the power of 2 minus pi k n squared. Okay. So the logarithmic energy cost is the same form as the logarithmic entropy gain that you have over here. And this precise balance will give you a value of k, such that if k is larger than 2 over pi n squared, this is going to be an exponentially large cost. There is a huge negative power of L here that says no, you don't want to create this. But if k becomes weak, such that the 2, the entropy factor, wins, then you will start creating these things. So you can see that over here, suddenly we have a mechanism along our picture over here, maybe something like k, which is 2 over pi, such that on one side you would say, I will not have topological defects, and I can use the Gaussian model. And on the other side, you say that I will spontaneously create these topological defects, and then the Gaussian description is no longer valid because I have to now really take care of the angular nature of these variables. Okay? So this is a nice picture, which is only a zeroth order picture, and to zeroth order it is correct. But it is not fully correct, because even at low temperatures, you can certainly create pairs of plus minus defects. Okay? And whereas the field for one of them will fall off at large distances, the gradient of theta as 1 over r, if you superpose what is happening for 2 of these, what you will convince yourself that if you have a pair of defects of opposite sign at the distance d, that the distortion that they generate at large distances falls off not as 1 over r, which is, if you like, a monopole field, but as d over r squared, which is a dipole field. So whenever you have a dipole, you have to multiply by the separation of the charges in the dipole, and that is compensated by a factor of 1 over r in the denominator. There is some angular dependence, but we are not so interested in that. Now, if I were to integrate this squared, you can see that it is something that is convergent at large distances. And so this is going to be finite. it is not going to diverge as the size of the system. Okay? Which means that whereas individual defects, there was no way that I could create in my system, I can always create pairs of these defects. So the correct picture that we should have is not that at low temperatures you don't have defects, at high temperatures you have these defects spontaneously appearing. The correct picture is that at low temperatures, what you have is lots and lots of dipoles that are pretty much bound to each other. And when you go to high temperatures, what happens is that you will have these pluses and minuses unbound from each other. So if you like, the transition is between molecules to a plasma as temperature is changed, or if you like, it is between an insulator and a conductor, and how to mathematically describe this phase transition in 2 dimensions, which we can rigorously, will be what we will do in the next couple of lectures.